Welcome back. Problem 12-34. So this problem is taken from chapter number 12, that is Deflection of Beam and Shaft, and book name is Mechanics of Material by R.C. Hibbeler. And we will solve this problem by using singularity function. So statement is determine the equation of elastic curve, the maximum deflection in region A, B, and the deflection of end C of the shaft. EI is constant. So you can see this is the shaft, and at point A and B we have supports which are bearings, and at this point we have P load that is downward, and at point C there is a P load which is downward. To this loading you can see the beam will deflect like this, and we have to determine the equation of elastic curve, maximum deflection in region AB, and deflection at end C of the shaft. So let's start with the solution. So if you remove the support at point B, you can see that you have to replace it by a reaction force, and this force is taken as upward and represented as RB. And similarly, if you remove the reaction support at point A, so you will be having reaction force which is RA. So we'll find this RA and RB by using equation of equilibrium. So first equation of equilibrium is sum of all moments about point B is equal to 0, and taking the counterclockwise movement as positive. So here you can see about point A, first movement is due to RA force which is upward, and the perpendicular distance is 2A, and this is producing clockwise rotation, so it will be negative. The second movement is due to this P force, and perpendicular distance is A, and this is producing counterclockwise movement, so it will be positive. The third moment is due to this P force, and perpendicular distance is 2A, and this is producing clockwise rotation, so it will be also negative. But their sum must be equal to 0. So I will write RA into A 2A, and that is negative clockwise, plus P into A which is counterclockwise, minus P into A is equal to 0. So PA and minus PA will cancel each other, so it means that RA is equal to 0. Now we will move toward finding the RB, and that can be found by using the equation of equilibrium, that is sum of all forces along y direction must be equal to 0. So I will write it, sum of all forces Fy is equal to 0, and upward force is taken as positive. So you can see that Ra which is upward, and that is 0. So 0, the second force is minus P, plus Rb minus P is equal to 0. So from here you will get Rb is equal to 2 times of P. So now we have RA and RB, so we will move towards singularity function in order to determine the equation of movement. So I will write singularity function. Why we use singularity function? Because for finding the equation of elastic curve by using equation EI into d square V over dx square is equal to moment. So by using this function we will find the equation of moments in order to determine this equation of elastic curve. And you can see the loading over here is point loading. So we will go to the table that is available in the book. I will go to the previous problem, and here you can see we have taken the second rows, and this is the load P that is applied at a distance of A. So for moment equation you can see moment is P into x minus A power 1. So I will copy it and we will paste or write it over here. So this is the moment equation. M is equal to P into x minus A power 1. Now you can see that at point A we have RA which is equal to 0. Clear? So what we will do is that due to this RA there will be no movement. So movement will be equal to 0 due to this RA. So let me write M is equal to 0. Now another load is P, and this is at a distance of A from point A, and X start from point A. Clear? So we will write it as minus P into x minus a power 1. Why minus p? Because let me go back to the table. This p is upward, so movement is positive. If p is downward, so movement will be negative. Okay. Now the third movement is due to this RB force, and RB force is upward. So plus 2p into x minus 2a. So this is the equation of movement, and we will left the right term and we will neglect it. So now you have this moment equation, which if you further simplify it, so this moment will be equal to minus p times into x minus a plus 2p into x minus 2. Okay, 2a. Okay, this is 2a, not not 2. Okay. Now put the value of this moment in this equation. So ei into d square v over dx square will be equal to minus p into x minus a plus 2p into x minus 2a. Okay. So if you integrate it once, integrate this equation once, so you will get ei into dv over dx will be equal to minus p times into x minus a power 2 divided by 2 plus 2p into x minus 2a whole square divided by 2 plus there is a constant of integration which is c1. Now this 2 and 2 cancel with each other, so I will remove it. Clear? So it will be p into x minus 2a whole square. Let this is your equation number 1. Now integrate this equation number 1 again. So you will get ei into v is equal to minus p times x minus a whole cube divided by 3 into 6, 3 into 2 is 6, plus p into x minus 2a whole cube divided by 3 plus c1x into plus c2. And this is your equation number 2. Now C1 and C2 are unknown constant of integration. So we will find them by using boundary condition. So let me write it. So boundary conditions are, the first boundary condition is that at x is equal to 0, we have deflection is equal to 0. So let me show it first. Here you can see at point A, x is equal to 0. So deflection will be equal to 0. So what we will do, we will put it in equation number 2, which is the equation of deflection. So put in equation number 2. So what we'll get is that you can see deflection is equal to 0. So this term will be 0 and x minus a will be minus a. So anything inside the Macaulay bracket which is minus will be considered as 0. So this term will be 0. Similarly, the second x minus 2a will be also 0 because it is negative. And c1 into x will be 0. So we will left with c2 is equal to 0. So this is C2 is equal to 0. We will apply the next boundary condition, and the next boundary condition is that at x is equal to 2a, deflection is equal to 0. So let me show you at point B, you can see x is equal to 2a, so deflection is equal to 0 because this is a support. Clear? So put it in equation number 2. So what we will get is that EI into V term. So EI into V is equal to 0. So EI into 0 is equal to minus P into 2A minus A power 3 divided by 6 plus P into 2A minus 2A power 3 plus C1 into 2A plus C2 is equal to 0. So this term EI will be 0 minus P times A cube over 6, and the other term will be equal to 0 as well, because 2A minus 2A is 0. So this term will be 0 plus 2AC1 So from here you will get C1 will be equal to PA cube over 6 multiplied by 2A, and C1 will be equal to PA square over 12. So we have the value of C1 as well. Now you have C1 and C2, so you can just put it in equation number 1 and 2 in order to determine the equation of slope and deflection. So we will put it in equation number 1, put the value of C1 and C2 in equation number 1. So you will get EI into dV over dx is equal to minus P into x minus a whole square over 2 plus P into x minus 2a whole square plus C1, which is equal to PA square over 12. Now divide EI on both sides of the equation, so you will get dV over dx is equal to 1 over E into minus P times into x minus a whole square over 2 plus P into x minus 2a whole square over plus PA square over 12. And if you take P over 12 as common from all the terms, so P over 12 EI is into the first term will be equal to minus P times P is, we have taken P as common, so minus 6 into x minus a whole square plus 12 into x minus 2a whole square plus a square. And this is the equation of slope. So dV over dx is equal to 1 over P over 12 EI into minus 6 times x minus a whole square plus 12 into x minus 2a whole square plus a square is, and let this is equation number 3, and this is the equation of slope. Since we are determine the equation of elastic curve and this beam deflect like this, you can see, so the slope in the region AB will be the maximum. And we will also find the equation of elastic curve. This is equation number 3, that is for the slope, and now we will put C1 and C2 in equation number 2 in order to get the equation of elastic curve, which is EI into V is equal to minus P into x minus a whole cube over 6 plus P into x minus 2a whole cube over 3 plus C1, which is PA square over 12 into x plus C2 is 0. And again, if you divide EI on both sides and take P over 12 common from each term, so you will get the equation of deflection is P over 12 EI into minus 2 times into x minus a whole cube plus 4 into x minus 2a whole cube plus a square into x. And this is equation number 4, which is the required equation of deflection, or required equation of elastic curve. And this is the answer of our part first, or part 1. Now we'll move toward finding maximum deflection in region BC. So you can see that this is the region BC, and we do not know the exact location where of x where this deflection will be occur. So x is greater than a and less than 2a. In this region, maximum deflection will be occur, and you can see that at maximum deflection we have slope is dv over dx is equal to 0. So I will copy this equation number 3, which is about the slope, and we will move toward next page. Let me copy it. So we will paste it over here. So at x is greater than a and less than 2a, we have maximum deflection, and maximum deflection means that dv over dx slope is equal to 0 at maximum deflection. So what we will do is that dv over dx, we are going to find out the x where deflection is maximum. So put dv over dx is equal to 0 in equation number 3. So 0 is equal to p over 12 ei into minus 6 times x minus a whole square plus 12 into x minus 2a whole square plus a square. Now you can see these are two terms and their multiplication is equal to 0. So it means that p over 12 ei is equal to 0, or this term is equal to 0. Since p over ei is constant, it cannot be equal to 0. So this term is equal to 0. So therefore 0 is equal to minus 6 times x minus a whole square plus 12 into x minus 2a whole square plus a square. Now you can see x is greater than a and less than 2a. So in first term, minus 6 times x minus a whole square will be not equal to 0 because x is greater than a. And the second term, x minus 2a. So x is less than 2a. So if you put x is less than 2a, so this term inside the Macaulay bracket will be negative, and negative anything inside the Macaulay bracket which is negative will be considered as 0. So this will be 0. So minus 6 into x minus a whole square plus a square is equal to 0. So when you solve this, you will get x is equal to 1.4082 times a. So this is the value of x, or location of x where maximum deflection occur. Now we will find this maximum deflection. So what we will do is that at this x is 1.0428, we will put it in equation number 3. So for that I will copy this equation number 4, that is about deflection, and we will paste it over there so that we can easily put the value of x in order to find the maximum deflection. So we'll paste it here. Now put x is equal to 1.402 into a in equation number 4. So this deflection V will be maximum, and that maximum deflection in region AB will be equal to P over 12 EI into 2 times minus 2 times 1.4082 A minus A whole cube plus 4 times into x minus 2A. X is 1.402A minus 2A whole cube plus A square into 1.402. 2a. Okay. So now the first term will be, the second term will 4 into this term is negative because anything inside the bracket, Macaulay bracket, is negative, considered as 0. So we will get maximum deflection in region AB. After calculation, you can do it by yourself. In region AB comes out to be 0.106 PA cube over E into I. Since this value is positive, it means that deflection is upward. And that is the answer of our part. So this is the maximum deflection in region AB, where x is equal to 1.408 A, and at this point we have maximum deflection in region AB. Now we will move toward, this is the answer of our second part, or B part. Now in part C we have to find the deflection at point C, and deflection at point C means that x is equal to 3 times A. So let me show you. You can see here that at here x is equal to 3A, we have this maximum deflection at point C, which is equal to VC. So put x is equal to 3A in equation number 4. So you will get VC, deflection at point C, is P over 12 EI into minus 2 times x minus, x is replaced with 3a minus a whole cube, plus 4 into 3a minus 2a whole cube, plus a square into 3a. Okay. So again, when you solve this, you will get deflection at point C comes out to be minus 3 times p into a cube over 4ei, and this value is negative, so minus 3pa cube over 4ei minus means downward, so deflection is downward, and that is the answer of our part 3, that is deflection at point C. So this was all problem 12-34, in which first we have find the equation of elastic curve, and then we will move toward finding the deflection at point in region AB, and then deflection at point C. And that was all about this problem 12-34. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also check the description box of every lecture. You will be able to find the playlist of every chapter where all the problems are mentioned. Again, if you have any question, you can ask me in comment section. Thank you for watching.